Okay, welcome to part 5 of our lecture from Wednesday, February 15th, where we're going to talk about exceptions to Aufbau using what we know about orbital stability based on their degree of filling. So as a reminder, any orbitals that are full or half full are going to be much more stable electron configurations compared to those that are not. So when we have this conversation about exceptions, we're really going to be focusing on our D block elements. So consider, for example, let's look at chromium. So just to identify where chromium is here. And using my noble gas shorthand, if I were just straight up following Aufbau, or the periodic table, going backward from chromium, my preceding noble gas would be argon. And then to fill in my outermost or valence electrons, that would be argon, followed by 1, 2, 1, let's see here, where's my laser? 1, 2, 3, 4, S, 2. And then if I were to keep going, this would now be my 3D, because I'm now my D block. 3D. 1, 2, 3, 4. So this is what we would expect or predict. From our periodic table. However, let's look at the orbital box diagram for the valence or outermost orbitals of chromium. So for S, that is a higher energy level, 4S, and then 3D. Remember, there's only one orientation for the 4S, and then 5 orientations for the 3D. So if I were to fill this in as written from the periodic table, this would be 4s2, 3d1, 2, 3, 4. Now let's pay attention here. This 3D orbital is incredibly close to being half full. It is only one electron away from being nice and stable. In fact, that stability is so desired by chromium that it's going to do something to achieve that stability. So instead of what we expect, what we see is the 3D orbital stealing a 4s electron to become more stable. In other words, half filled. So if I think about what that might look like, if I've got my 4s and my 3D, that would look something like this. The 4s would have one electron taken from it, And instead of having 3D4, 3D4, I would now have 3D5, where the electron that was once in the 4s has now been stolen to go into the D5. Now, why is that okay? Like, why is that something that nature allows to have happen? Because wasn't the 4s full and thus stable? Well, remember, we want our valence orbitals, which are these guys, to be stable in the sense that they have either totally half full or totally completely full valence orbitals. So in cases like chromium, where we are only one electron away from being completely or more stable, I should say half full, then we're going to take an electron from the prior filled s, because now when we do that, notice the 4s is half full, which is a stable orbital configuration. And the 3D is now totally half full. So this is nice and stable. So any d orbital that Aufbau predicts would have a d4 will always steal an electron from the prior filled s. Now, it's not just half full orbitals that are much more stable. It's also totally full orbitals that are much more stable. In fact, those are way more stable even compared to half-filled orbitals. So it's not just the D4s that we got to look out for. So for example, let's look at the electron configuration of copper. So using my noble gas notation, copper's in the same row as chromium, so it's going to have the same prior noble gas, which is argon. And that would be 4s2, 3d9. Count 1, 2, 3, 4, 5, 6, 7, 8, 9. And again, this is what we would expect from the periodic table. However, if I were to draw my valence configuration here, looking at my 4s and my 3d from this periodic table prediction, I would have 4s full and 3d 1, 2, 3, 4, 5, 6, 7, 8, 9, which means that this is only one electron away from being 100% full. meaning its 4s would be totally full, and its 3d would be totally full. So the same thing happens. So again, the d orbital, d9, steals an electron from the preceding s orbital to become stable by being totally and perfectly full. So instead, we would see an electron configuration for copper of argon 4s1 3d10. We're looking at our orbital box diagram. We would see 4s1, which is half full, and 3d 1, 2, 3, 4, 5, 6, 7, 8. Let me make myself some more room to draw this. 6, 7, 8, 9, 10. There we go. So here we have 4s, which is half full. So it is stable. And then we also have now our 3d, which is completely full, which is even more stable because it's got every single orbital totally and completely full of electrons. So anytime we are looking at D4, but also D9 elements, they will do the same thing by taking an electron from that previous s orbital so that they can become more stabilized. Okay, so we got to look out for the D4s as well as the D9s. Now let's have a quick chat about f orbitals. Because there's a couple of different accepted ways to write the f orbital configuration. And the exceptions are not ones that I'm going to ask you to know because they're really complex and hard to explain, at least in this level of chemistry. So you'll remember I said that these elements here constitute the D block, and these elements here the F block, because we have these things that have been recessed or pulled out of the periodic table. So this is kind of hard to see, that recession or that pulling out from the periodic table. So let's look at the periodic table with the F block elements added back in. So I'm going to do that down here. So the reason why we pull those F-block elements out is because otherwise the periodic table would have this kind of gnarly shape here. It wouldn't be as compact. So let's see if we can't get a kind of comparison here. Not great. So if I were to follow Aufbau here, like let's go back to our example of PR. From our regular periodic table, so from here, we had an electron configuration that was xenon, 6s2, and then 4f3. So here that would be 6s2. Here we're now officially in the D block, 41, 2, 3. That's what we got from our periodic table. However, technically, lanthanum and actinium are D block elements. So technically, it is more appropriate to fill one electron in our prior D orbital before filling the F, based on the true structure of the periodic table given here. So if we were to do that for, again, PR, going all the way back to the first preceding noble gas, that would still be xenon. This would be xenon. Okay, after xenon, I am in 6, so 6s. But then notice when I hit lanthanum, I'm in my D block, and my D block starts in 3. So it would be 3, 4, 5. 5D1, and then remember my lanthanum, lactanides and actinides, my F block, that's receded one further, right? This is 4 starting here. So this would then be 4F2. So this is the more correct version of the F block electron configuration. Always fill your D and then your F, and then go back and fill your D. However, I'll accept both. Now, let's see here. Just to kind of compare for your sanity, let's just check these against one another. They should still yield the same number of electrons. So xenon 6s2, 5d1, 4f2 from the more correct version, and then xenon 6s2, 4f3 from just our normal periodic table. We were to count these up, 1, 2, 3, 4, 5. We have 5 valence electrons, or electrons that are found in our outermost orbitals. And same deal here, 4s2, sorry, 6s2, 4f3, 3, 4, 5. That still gives us 5 valence electrons. So when we start looking at some properties and trends in our F block metals, we're going to have to think about whether this or this is more correct, even though it's going to get really complex. Like I said, if I were to ask you to give me the electron configuration for an F block, you can give me either. Not sure what active chem will accept, but both are technically correct. But the main idea here is we gotta watch out for these D4 and D9 elements, because they will always become a D5 and a D10 with the previous S being an S1. Okay, let's see here. We've done our exceptions to Aufbau. I don't think I have time, unfortunately, despite how much I'd like to keep going, to do our electron configuration of ions. So we will save this for Friday, meaning that all of this is going to be the end of material that you will see on midterm 1 next Thursday. If you need help answering these questions that deal with electron configurations of ions, in general, the rule is if you add electrons, you follow Aufbau. So just keep going like you normally would. If you remove electrons, then you remove P, then S, then D, then F. That's the removal order. But again, we will talk about this on Friday together.